It's just so I'm going to video this just so you guys have two different ones. You could look at this one or even chapter or period 3, because I might do something here that makes things a little bit better. Who knows? So a logarithm is based off of the exponential function. Okay, and the exponential function is made up of a base and an exponent. Okay, and so that's the whole power. Okay, the power is a base and an exponent. And so when we're talking about a base and a power, we have a base of 5 with an exponent of 2, and that equals 25, right? Okay, and so we have a base and an exponent and a number. Okay, and when we talk about the log, what we want to do is put that log base on the log. So the base goes on the log. The number, okay, comes here, 25. And it equals an exponent, which is 2. Okay? And so what this does is it allows us to set this up as the log of the base, right, of the number is equal to the exponent. Okay? And this is the key to logarithms. This is what lets you manipulate logarithms. Okay? Now, I showed that key earlier as this. Log base b of x is equal to a. Then, b to the a is equal to x. Right? And you have the base b to the a. And that's how I showed it earlier. I used to show it in the past like this, and I didn't get to show it till later. We were working on the homework already. Okay? So I'm kind of going back a little bit with you guys and showing you another way of looking at this. Okay? And so when you think about logarithms, you want to think about the base is raised to the power to get you the number. And the reason we do this is because it's not always neat. Okay? What I mean by neat is the log of base 3, okay, of, say, 4 is 81. Okay? That's neat. That's neat because, well, 3 raised to the 4 is what? 81. Okay? So that's nice and neat. Yay. But it's not always nice and neat. Okay? Sometimes, like yesterday, we were doing those problems where we were saying, hey, when we take this exponential function, how am I supposed to find out when we're going to be done with, we had the decaying sugar, right? And we were like, well, when are we going to be down to only 10? Or when are we going to be from 10 units down to 5 units? And now you can plug that into a logarithmic function and find out exactly when. Okay? And that's what we need to do whenever we're dealing with decay, especially with something like insulin, right? Or any kind of medical thing, right? Not to mention isotopes and radioactivity. We want to know when it's going to be safe to go in there, all right? You know, a lot of radioactive decay takes millions of years, but some of it goes actually quite quickly. So you can actually enter the room in a certain amount of time. But if you enter that room before that time elapse, you're going to die if you're not covered, right? So these are the things that we use it for as far as for decay, right? But also we want to learn, okay, well, how about when, you know, my muckleshoot money's going to be $1 million? You know, how do I know that? Well, we can throw it in that also. We can figure out exactly when it's going to be $1 million. So when you're, you know, 42.3 years of age, okay, then you say, okay, I'm 42 plus 3 years. Okay, so 0.3 years means, you know, a third of a year, a third of 12 is 4. So 4 months after I've turned 43, I'm going to be able to pull out that $1 million. Okay? Or whatever it is. So this is the reasons why we do this. Okay, we need it to be exact. Okay? So it's nice when it's neat, but it's not going to always be neat. And so that's why we use logarithms. Now, what we're going to be doing today is basically doing a lot of this. You're going to change logs to exponential functions, and from exponential functions to logs. Okay? So you can go back and forth. Okay? So that's this part. Some of the things you're going to do is like this. This is another rule. So if I have this log of 25 base 5, right? Well, that's nice, but I can't plug that in the calculator. Because your logarithms in your calculator are made up on base 10. They're made up of base 10 because 50 years ago, we came up with this device. Okay? And this is a slide rule. And you use this slide rule to deal with a lot of things, and one of those things is logarithms. Okay? This is what they had on Apollo 13 to be able to figure out how they're going to get around the moon. All right? These calculations saved their lives. Okay? This little machine right here. Okay? So this was their calculator. Okay? So without it, they had people doing calculations for them in Houston. But what happens when that communications goes dead? Like when they go around the moon. They have to do it on their own. They had to make adjustments on their own when Houston wasn't available for them to be punching it into their calculators and their computers and all that stuff. So they had to use their own computer. Because did you know that the computer that was on Apollo 13 is actually less valuable than this? It couldn't do what this can do. That's the amount that computer on Apollo 13. The functions on that Apollo 13 were basically to just fly the plane or the ship. Okay? So the adjustments and all the calculations were done here and here. So what I'm saying is this had to be made with one type of logarithm. So what they did was they did base 10. Okay? Because we're on a base 10 system. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Right? So base 10, 1. Right? Even though a lot of Native Americans were base 20. Right? Some were base 5. Chinese were base 8. Okay? There's a lot of different bases out there. Your computers nowadays are all base 2. Okay? So there's a lot of different base systems, but the one that won overall was base 10. And so that's why they use base 10 as their logarithm. So whenever you see a log on your calculator that says log, it's going to be base 10. Okay? But that says base 5. How am I supposed to put that in my calculator? So we have a rule. And I call it the underline rule. Okay? It's that simple. I underline it and I put my log. Okay? Now you can make it complex. The log base b of x is equal to log x over log base b. Or log b, sorry. Okay? But you can call it the underline rule, and basically it's just log 25 divided by log 5. And if you plug that in your calculator, you will get 2. Log 25 divided by log 5 equals 2. Okay? And so, if you're given something like log of 3 base 2, right? I can plug that in the calculator as log of 3 divided by log 2. And what do I get? Oh, I have to have a calculator. So, if I put log of 3, hit equals, and then divide by log of 2, and hit equals, I get 1.58. Okay? So what that's telling me is that 2 to 1.58 is equal to 3. Okay? But it's 158, blah, 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 right? Because it's an irrational number that goes on forever. All right. So, this is how we deal with that part of the calculations. Does that make sense? So it's just, if I want to change it into log 10, log base 10, I just do the underline rule. And now they're both in base 10. Cool? All right. After that, I need to also realize that I don't have to just change it in the base 10. I can change it into any base I want, as long as they're both the same base. So instead of saying it's base 10 and base 10, I could say, like here, I could say log base 2 of 25 over log base 2 of 5 is still going to equal 2. Now, I never used this before in my life because my base system in my calculator is base 10. So I always use base 10. Later on in pre-cal and cal, you might end up having an equation where it's equal to log base 2 of something, so you'll have to do that. Okay? But for now, I don't think it's going to be necessary. Okay? So for now, I would just worry about pushing it to base 10. Okay? The next thing. Let's talk about that base 10 for a minute. When you have any number, right? Log base b is equal to 0. Okay? We got to think about that. Okay? B to the 0 is equal to what? Any number raised to the 0 is equal to what? No, not 0. 1. And so that's why log of 1 of any base is going to be 0. Okay? So you got to keep that in mind. So this is a rule we're going to use. Okay? It's an identity rule. So log base b of 1 is equal to 0. Then that means that b to the 0 is equal to 1. Okay? Now with that said, we're going to get into logarithms, natural logarithms. Okay? Now natural logarithms are not base b. Okay? You can have any base in the world, right? But the natural logarithms are base e. Now e is a number that comes up in nature all the time. You may recognize this kind of shape, right? If you look at a snail's back, a shell, you'll see this shape. If you look inside a sunflower, you'll see this shape. If you look on a pine cone, you'll see this shape. This shape comes up throughout nature, all over the place, okay? E is a relationship that we found. It's called the golden ratio, okay? And so it's a number that comes up a lot in nature, okay? And so we use this base E a lot. And we use base 10 because 10, 1, right? So we use base 10. We also use base E. But instead of getting them confused, we call this the natural logarithm. So it's the natural logarithm is spelled Ln. Okay? So you'll see that come up in nature, in your forestry classes, hopefully a lot. Okay? The further you get into biology, the more you'll see the relationship of E coming up. Alright, so we need to know the natural logarithm. That brings us up to the whole, well, what is E to the 0? Well, any number to the 0 is what? 1. So I can bring that backwards and say, then that means Ln, because log base E, right, of 1, right, is equal to the exponent, which is 0. So the logarithm of 1 is also going to be 0. Okay? As we go forward, then we also want to talk about identity. If I say the log of 2, right, of 2 is equal to 1, what am I saying there? I'm saying that this 2 to the 1 is equal to what? Well, what is 2 to the 1? 2 to the first power? 2 times 1 is 2, right? 2 to the first power is just 2. That's all this means. 2 to the first power is 2. That's it. Okay? So I want to have that anytime I'm taking the log of a number of the same base, it's going to equal 1. So log of 13 of 13 is going to be 1. Log of 15 of base 15 is going to be 1. Log E of base E is going to be 1. So therefore, the ln of E is going to be 1. That's it. Okay? Now, we get to the harder stuff. Okay? This isn't that hard though. Think about this. Think about this. If I have x to the 5th times x to the 3rd, what do I get? What is that? X to the 8th. What did you do? You added the exponents, right? So anytime you multiply two powers with the same base, you add the exponents, right? What is a logarithm? Right? The logarithm is the exponent, right? So since a logarithm is an exponent, right? Anytime we're going to add the exponents, we're going to, what? Multiply the bases. So what that means is, if I say log of x plus log of y, then what I'm going to say there is, because we're adding the exponents, logarithms are an exponent, we're adding the exponents, then we're going to do what? Multiply. So this is going to be log of x, y. Okay? So we're going kind of backwards. Okay? If we're multiplying the bases, we add the exponents. If we're multiplying in here, we're going to add the exponents. We're going to add the logs. If we're adding the logs, we're multiplying the bases. Okay? The whole power. Okay? Alright, so that's our addition rule. Subtraction. Well, what do we do when we divide? If I have x to the 5th divided by x to the 3rd, what do we do? What is that? Yes, you subtract. So what do you get? X to the 2, right? Then all we do, log of x minus log of y is what? That's it. Not log of x divided by log of y, but x divided by y. We just take those two powers and divide them. Okay? Those two numbers are going to be divided. In the same